In this video, I will talk about simple harmonic motion for a physical pendulum. First, let's look at what is a physical pendulum. So it comes from rigid body. The meaning of rigid body is that such an object does not change its shape during a motion. And if you're not familiar with this concept, you can review the sections, the previous sections about rigid body. Okay. So here is an example of rigid body. Let's say this rigid body has some arbitrary shape, and the center of mass is at this location. Let me use a cross sign to represent center of mass. Now this rigid body is rotate around a rotation axis that is fixed at this location. Okay, so that's rotation axis. And I can also draw a vertical direction through this rotation axis. And I want to use this vertical direction as the reference direction. And also it's the equilibrium position. And the position right now you see for this rigid body is already away from the equilibrium position. And you can imagine that there's a force to pull up this rigid body, rotate it along this rotation axis to this new position. And then we'll let this rigid body go. Then it will start doing rotation back and forth around this equilibrium position under the force of gravity. Okay, so let's draw a free body diagram for this rigid body. Gravity is acting at this center of mass. So that's mg. M is the mass of rigid body, and that's all. That's all the force we have acting on this rigid body, and the driving force for the simple harmonic motion is this gravity. Okay. But because we are talking about rotation, so now let's think about the torque due to the gravity with respect to the rotation axis. So we need to draw a vertical line from rotation axis to this gravity direction. And this distance is level arm. Let's call it R. Okay. Now we have another distance here. I want to use the symbol D for the distance between rotation axis and center of mass. So this distance is D. Alright, so let's also use this angle between vertical direction, the equilibrium position, and the line connecting rotation axis and center of mass. I want to use this angle as the displacement, as the angular displacement for the rigid body. Let's call it theta. Okay. Again, this distance is d from rotation axis to the center of mass. Okay. Now the torque due to gravity is given by the lever arm R times gravity mg. Okay, and this torque is trying to reduce the angle theta here in this clockwise direction. So let me add a negative sign here. There's a sign convention for torque. If the torque is counterclockwise, then it's positive. That's this way. But if it is clockwise this way, then it's negative. So that's why that's a negative sign. According to Newton's second law for rotation, the torque here, tau g, is the net torque acting on the object, and that equals I times alpha. I is the moment of inertia with respect to the rotation axis, and alpha is the angular acceleration. Alpha is given by the second derivative of angle theta with respect to time. And the moment of inertia is with respect to the rotation axis. And there's a parallel axis theorem. It says that this moment of inertia equals moment of inertia of the center of mass plus moment of inertia plus a constant term m times d squared. So d is the distance between rotation axis and the center of mass. That's the symbol that we defined earlier. So this one again is called the parallel axis theorem. And if you do not remember this theorem, again, you need to check the literary body chapter. There's a discussion about this parallel axis theorem. Okay, so now let's see what kind of equation we can get for the to derive the simple harmonic motion. Okay, so the torque is R times mg and that is given by d, because R here will change. So if the literary body swings down, then its R becomes shorter. So it will change throughout the process. And we don't want this one as the changing variable in this Newton's second law equation. So I want to use the angle theta to represent this level arm R. So let's think about this relation. So the d here is a constant. D is a fixed number as long as this axis is fixed and the center of mass we know is fixed at this location. So d is a constant. But now R is given by d times sine theta. Okay, so that's the torque. And we need to add the negative sign here. That equals I times second derivative of angle theta. Alright, so that seems to be very similar to the simple pendulum, simple harmonic motion equation. And to get to the simple harmonic motion, we need one approximation here, just like in the simple pendulum case, small angle approximation, small angle theta. Then we have sine theta approximately equals theta. Okay, so now the equation becomes negative dmg theta equals I second derivative of angle theta. Let's rewrite this equation to the standard simple harmonic motion equation. So we have d theta dt second derivative plus dmg over I times theta equals 0. So the angular frequency is given by omega equals square root dmg over I. So that's the angular frequency for a general rigid body And let's think some specific example. Let's say rigid body here is a rod, and rotation axis is at one end of the rod. Now the center of mass is at the is in the middle of this rod, and suppose the total length of the rod is capital L. Now we know that the moment of inertia with respect to the center of mass here is 1/12 ml squared. M is the mass of the rod. And with respect to this rotation axis, their I is 1/3 ml squared. In fact, we just need to use this one. Okay, we don't actually need to apply this parallel axis theorem. But if you do, you will still get this moment of inertia. Okay, so let's look at this example of rod. Then omega equals square root. D is 1/2. Suppose the mass distribution is uniform, so D is L/2. So we have L/2 mg divided by 1/3 ml squared. So that gives us 3g/2L. That's the angular frequency of a rod rotation, simple harmonic rotation, and oscillation, simple harmonic oscillation. And if I compare this one to the simple pendulum, so for the simple pendulum, its angular frequency is square root g/L. So now we see there's an additional factor 3/2 in the physical pendulum. Okay. All right.